Hello students, and in this video we are going to talk about triangle inequality. Yeah, and then we'll go from there. Inequality. So this is another topic which is very important in this context. And what does it say? So the idea, let me just start with an idea first. Let's say this is your home, right? H, this point, and that point in complex plane, that is your school, S. Now, assuming that there is nothing in between your school and your home, so you can just move around from your home to school without any interruption in a straight line, right? Once you go to a straight line, this is the shortest possible path you can take to reach school or to reach home, whatever. Okay, now let's say that your friend where he lives here somewhere. So let me put it here. C. Okay, your friend C. He lives here and he wants to, you want to visit his home on your way to school. So essentially what you are going to do is you are going to take this path and then you will go this way, yeah, to school. So you can go straight from home to school in this path. But now what you are going to do is you are going from home to your friend's home and then from there to school. Yeah. So, and intuitionally speaking, it is quite clear that you are actually taking the longest route. This is not the shortest route to reach home, right? So you are going via your friend's home. So you are taking a much longer route than the shortest one. Okay. So what we have is, so this is what triangle inequality says. Yeah. So what it says is, essentially it says that if you have, if Z1 and Z2 is in C. Yeah, so they are complex numbers. Let me write it properly. Are complex numbers. Okay, now if they are there, then what happens is, if you look at mod Z1 plus mod Z2, yeah, mod Z1 and mod plus mod Z2, then that is always getting dominated by mod of Z1 plus mod of Z2. Okay, so this is the shortest path. You see, mod of Z1 plus Z2 is basically the distance between origin and Z1 plus Z2. Yeah. So if you want to reach something like this, let's say this is your Z1 and this is your Z2. See, the thing is, this is Z1, this is Z2, and Z1 plus Z2 is somewhere here. Z1 plus Z2. So you see, this is the distance from here to here. This is the distance, this one. Yeah. So that, what the thing is, this what you are saying is essentially this is always getting dominated by the distance from here to here and the distance from here to here. Okay, that's what it says. Okay, so how do you prove something like this? Let's just understand this thing. Yeah. Okay, proof. And of course you can see that if Z1 and Z2 are both 0, then the equality definitely holds. Yes, so that is there. Okay. Now, how to look at the proof? Let's say this sort of proof, always do it like this. Complex things are much easier if you look at it. So, like this. Let's say you take a square of this thing. Okay. So, what is it? This becomes, you remember, mod Z square is Z bar, right? So, Z1 plus Z2 and Z1 plus Z2 bar. Z2 bar. So, that will give you Z1 plus Z2 and Z1 bar plus Z2 bar. Clear? That will give you Z1 Z1 bar plus Z1 Z2 bar plus Z2 Z1 bar plus Z2 Z2 bar. Okay. So now, see, this is nothing. This part is nothing but mod Z1 square, the first one. The second one and the third one, these two things, what we will do is this. See, if you look at it properly, Z2 Z1 bar can be written as Z1 Z2, okay, bar, the bar of that, right? Yeah. So the okay. So what I will do is this. I will write it like this: Z1 Z2 bar plus Z1 Z2 bar, the bar of the whole bar, something like this. So essentially, I am saying bar. You think of it like I am doing conjugate, right? Well, you know that. But so I am saying it like a bar plus mod Z2 square. Yeah. Why this whole? Since Z square is nothing but Z1, Z2. Z bar. Z bar. Clear? That is why I can write it like this. Yes. Okay. And of course, Z bar, the bar of that is nothing but Z. Yeah. So essentially, you take z, you take the conjugate of z, and then take the other conjugate of z, then you end up with z itself. So that's what we are using. So now these, you see, you can write it like this: mod z1 square plus mod of z2 square. Yeah. And this particular thing, if you remember, you see, if you take z1, z2 bar as, let's say, a w, which is in C. So you have w plus w bar, right? That is what this, this particular thing says. So that is nothing but 2 times real part of w. This is what we did in the last videos. Okay, so we are going to use this thing. So this becomes plus 2 times real part of z1 z2 bar. Yeah. Okay, I hope this is very clear here. Yeah. Now you see, there is this very simple inequality. Think of it like this. See, z is what? X plus iy. Yeah. So, and mod z is what? Mod z is nothing but x square plus, so mod z square is x square plus y square, right? Yeah. So you see, x square is what? X square is real part of z, the square of that, right? And y square is what? It is the imaginary part of z, the square of that. So this is always getting dominated by mod z square. This is also getting dominated by mod z square. So basically, you see, the real part of z is always getting dominated by mod z square, and the imaginary part of z is always getting dominated by mod z square, right? That is always true. Okay, so I'm going to use this in fact. So this less than equals to mod z1 square plus mod z2 square. Okay, plus, you see, I will dominate this part, so I will write it like this. This is mod z1 z2, the power of that. This is okay. Yeah. Now the thing is, you see here, this is what we are going to use here. So we are taking the multiplication of those two things, and we don't know what to do here. You understand how to? So the basic logic says that if z1, z2, the bar or the modulus of that, we want it to look like this, yeah, but we don't know if it does or not. This is the part which we are going to do in the next section, and this is why we need this. You understand? Because in daily calculations, this sort of thing is very important. Okay, so what for now I am not going to. So I'm going to assume this thing, and I'm going to write it like this. You see, this becomes mod z square plus z2 square. This particular thing you can write it as mod 2 times mod z1 times mod z2 bar. You can do that. Yes. Okay. So essentially, you see, z1, z2, the bar of that is actually equals to, this is not equals to, this is equals to. So essentially, I am using this particular thing. Mod z1, z2 is equals to mod z1 times mod z2. This is always true. Yes. I did not prove it. I will do it in the next section, next part. Okay, so this is why you understand why this next part is very important, because we have, if we want to prove something like this, we need this. So you see, now what is mod z2 bar? You see, mod z and mod z bar is essentially the exact same thing. You can check this. Yes, please check this. Very simple. Now what we are going to do is, so this is simple, and I can write it like this. This is nothing but mod z1 plus z2. Okay. z1 square plus mod z2 square. This is what I get here. Yeah. Plus 2 mod z1 mod z2. Yeah. Which is nothing but mod z1 plus mod z2, the square of that. So therefore, what do we get? Mod z1 plus mod z2 is dominated by mod z1 plus mod z2. Here, which is the triangle inequality. So this is what we need to show. Okay. So very simple thing, but the thing is, this actually gave us the idea that we somehow need to know how does the modulus and the multiplication actually works, and what does multiplication means essentially geometrically. See, addition, you know, right? So if z is here, z2 is here, you can add it and you are going to get somewhere here. So essentially, this is z1, this is z2, that's your z1 plus z2. This we know. Now, but in this is from your R2. But what about in R2? Let's say if you have two vectors, let's say A and B, can you multiply those two vectors? You can't, right? So there is no, it doesn't make sense to have a geometric idea of what multiplication of vectors in R2 is. But here in complex, you can multiply two complex numbers. So we are going to understand what is the geometrical interpretation behind this complex multiplication. So what we are going to do is we are going to do complex multiplication. Okay, the geometric interpretation, basically complex multiplication. Okay, you have already seen a property of complex multiplication. We are going to exploit that property here. Okay, so first thing first, let's say Z1, I start with a Z1, and in this case I will start with a polar thing, which is much easier to do. So it is R1 cosine theta 1 plus I sine theta 1, and Z2 is R2, okay, cosine theta 2 plus I sine theta 2, sine theta 2. Clear? So these are the R1 and R2 which we are working with. Now I need to, therefore, what is Z1, Z2? I need to see the multiplication of Z1 and Z2. Now this multiplication rule we already know. Yeah, please check this part up. Please check this, that this multiplication turns out to be this R1 times R2 cosine of theta 1 cosine of theta 2 minus sine of theta 1 sine of theta 2. Yes, this and this I'm just multiplying and I'm putting it here. Yes, if you are not convinced, please check this part. But this is just the multiplication. Sine of theta 1 cosine of theta 2 plus cosine of theta 1 sine of theta 2. Yes, that's what we are getting. So if you write it properly, it becomes R1 and R2. You know this is the formula, right? This is cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Very nice looking formula, right? Yeah. So you see, if you take the, if you take the absolute values of this product, if you take the absolute value, what happens? Therefore, mod Z1, Z2, if you take the absolute value, then you have to take the absolute value of this one, R1, R2, cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And you know what that is, right? Theta 2. So that is going to give you R1 times R2. Here. And what is R1 times R2? R1 is nothing but mod Z1 and R2 is mod Z2. So essentially, hence mod Z1, Z2 is nothing but mod Z1 times mod Z2. That is the, you see, this is the property we used. See, this is the property we used. Here. Now, the thing is this actually also gives us a very, very nice thing. Yeah. What about the argument of this product? See, the argument, if you look at the argument of Z1 and Z2, Z1 and Z2. Okay, just this general argument, that's what. So this is nothing but, if you look at it, you see, look at this formula. So 1, let's just call it. So argument of Z1 and Z2 is nothing but theta 1 plus theta 2, right? That is what other argument is. So what is theta 1? Theta 1 is the argument of Z1 and theta 2 is the argument of Z2. So argument of Z1 and Z2 is nothing but argument of Z1 plus argument of Z2. Yeah. So this is a very, very important property, and this is of course up to 2 pi multiple. Up to multiples of 2 pi, whatever you want to write it, please write it like that. So that's your thing. So argument of Z1, Z2 is nothing but argument of Z1 plus the argument of Z2. Yeah. And similarly, you can also talk about divisions. Yeah, divisions. Just 1 second. Yeah, divisions. So what is it? Division is, see, if Z1 and Z2 are two complex numbers like that, and Z2 is not 0, of course not, right? 0 means it's complex, essentially complex 0. Then you see Z1, the complex number Z1 can be written as Z1 by Z2 times Z2. Yes, we can write it like this. Yes, and so all of this is valid, right? Because Z1 and Z2 is defined. It's a well-known defined complex number, and then I'm multiplying it by Z2, and that will actually give us a Z1. Yeah? So that will imply that mod of Z1, what is mod of Z1? It is mod of Z1 by Z2 times Z2, right? So it is the product of two complex numbers multiplication. So it is Z1, Z2 times Z1 by Z2. So you see, therefore, what happens is mod of Z1 by Z2 is nothing but mod of Z1 by mod of Z2, right? So you see, multiplication, division is also very simple, that you just do it like this, yeah. Now, and what does this also give me? This gives me the argument of Z1 by Z2, Z1 by Z2, yeah. If you write it down, you can always see that you can check this, please check this part. This is nothing but argument of Z1 plus argument of Z2. So argument of Z2, therefore. Yeah. Why is this true? See, I mean, if you want to write it this way, you see, argument of Z1. So you see, why this is true? Let's just do it. Argument of Z1 is equals to argument of Z1 by Z2 plus argument of Z2. Yeah, from here, from 2. Okay, so from 2. Now you see, that is why argument of Z1 and Z2 is argument of Z1, sorry, minus argument of Z2. I made a small mistake here, minus argument of Z2. Clear? Okay. So what does this geometrically means? Let's just understand this thing, yeah. See, let's say Z1 is an element here, yeah, and Z2 is another thing, which is, let's say, Z2, yeah. So you see, let's call this as theta1, call this as theta2, the argument, theta2. So Z1 times Z2, what happens is this, see, what is going on with the length of Z1 and Z2? See, any complex number is defined using two things. One is the length of the complex number, R, which is nothing but mod Z, yeah. So that length. So first of all, what happens if you multiply Z1 and Z2? What is the length of Z1 and Z2? Basically R1 times R2, right? So the length gets multiplied. So here, let's say the length here is mod Z1, mod Z2. So Z1 times Z2, the length will get multiplied here. It becomes Z1, Z2. The length is something here, yeah. What about the argument? The first argument is theta1, the second argument is theta2, and here the argument of Z1 and Z2, you see, argument of Z1 is argument of Z1 plus argument of Z2, so theta1 plus theta2. So this angle here, it will be theta1 plus theta2. You understand? Yeah, I mean, I am just drawing it like this, but you get the idea of it, right? What I am trying to tell you. So that's the thing. So geometrically speaking, this is what the multiplication of two complex number looks like. Yes. Okay. So now let's look at a very, very important, applications of these complex numbers. Okay. So what is it? See, there is something called de Moivre's theorem. De Moivre's theorem. Of course, please remember, this is true up till 2 pi multiple. Again, all of this, because this is a general argument, this is always 2 pi multiple. Okay, so the equality holds. Now, the thing is this, I want to talk about another section, which is the integer power of z. So, you see, if z is there, z squared, z cube, we want to define something like that, right? How do we do that? So, to do that, we employ something called the de Moivre's theorem. Okay, de Moivre's formula. Okay, de Moivre's formula. So, how do I do that? See, let's say I am taking z1 equals to z2 equals to z. If I do that, yeah, then what do we have? Z. If you just look at it like this, you see z square, yeah, that will be z square, z times z. That is what we are going to call it as z square, right? Z square z. So this is z times z. Yes. Okay. So what is it? It is essentially, if you want to write it down, it is the what is the length of this thing? It is r times r, which is r square, right? And then what happens to this argument? It is let's say the argument here is theta. So essentially, let's say z is r cosine theta plus I sine theta. Yeah, we start with this thing. So z square. So the mod of z times mod of z. Yeah, you see here. You see, R1 times R2, and R1 and R2 are same. So R1 times R2 is R square essentially here. And here argument is theta 1 plus theta 2. Here both are thetas. Theta 1 and theta 2 is equals to theta. So that will give you cosine 2 theta plus I sine 2 theta. Clear? So you see, z square is nothing but R square cosine 2 theta plus I sine theta. And the thing is this, you can use induction. So you have to do it yourself. It is very, very simple. Please do it. Yeah. So you can use induction to show that for n greater than equal 3, doesn't really matter, 3, 4, 5, 6, you can go on doing this thing. Z power n, yeah, will always be written as R power n cosine n theta plus I sine n theta. Is it okay? You can always prove this. Yes. Okay. So that is what this is. And if you want to write it properly in another, so let me write down the de Moivre's form now. So once you do that, you see, for mod z equals to R, and let's say R is equals to 1 on the unit ball. Yeah. What happens is this formula, let's just call it 3. Then 3 becomes 3 says cosine theta plus I sine theta. Okay. Yeah. See, R is equals to 1. So power n, z power n, cosine theta plus I sine theta. R is equals to 1. So z becomes cosine theta plus I sine theta to the power n. That is nothing but R equals to 1. It becomes cosine n theta plus I sine n theta. Yes, that is the de Moivre's theorem. I hope this is very clear to you. Okay, now another question. I just want to put out a question here. So one question, this is for you to answer. So if n equals to n equals to 0, 1, 2, or of course this is true. What about n equals to -1, -2, -3? Yeah, is 3 valid? That is my question. Yeah. So you can think about it, and the answer is, what do you think the answer is? Yeah. So I am not going to tell you. Please do that and think about what we talked about, all these arguments and all, just in the other section. Yeah. You can use this and you can deduce the thing. Okay. So once that is there, we are going to now talk about something called the roots. Very, very important now, roots. This is one of the fundamental things in complex analysis. So what we have is this. Now let's say if z is w power n, yeah, w is a complex number, and let's say n is any natural number 1, 2, it can be any natural number. Yeah, so w to the power n by our de Moivre's theorem, you can see that what happens is that is also a complex number. Yeah, so let's just call it z. Yeah, so you see, if z equals to w power n, what does that imply? That implies that for each value of w, so essentially w is in C, right? W is any arbitrary complex number. It can be 1 plus I, it can be I, it can be something else also. So for each value, for each value of w, okay, there exists one value of z. Is it okay? One value of z. So you see, if you put a particular w, there is exactly one value of z, right? Okay. Now the thing is this, the question is this, can we talk about the inverse of this thing? Is it okay? So you think about it this way, x square equals to y. Yeah. If I put a value of x, you are going to get a unique y. But the thing is this, if I give you a y, how many x's are there? That is the question, right? You remember in the very beginning of this course, we talked about this question. X square equals to 1. Given this y equals to 1, how many x are there? That is how we end up with here. X equals to -1, right? Y equals to -1, how many x are there? This is the question we wanted to try. Here also exactly the similar sort of thing. Now the question is this. Question. Given z in C, yeah, can one find w? Can one find w? Yeah. And is this W unique? Of course not. It's not unique. You do realize that it's not going to happen. Yeah, even in real also it is true. But the thing is, we just want to find out what exactly can we do from here. Yes. Okay. See, the thing is this: if Z equals to W power n, let's just call it 4. Yeah. So we actually will show that there are exactly n roots of Z. Okay. So we'll call it the values of W. So, sorry, the values of Z which satisfies Z equals to W power n. Okay, that we will call as the nth root of Z. Okay, so you see, each of this W is called, we will call it the nth power of Z. Is it okay? Yeah, and denoted by W equals to nth power of Z. Yeah, this is our simple, whatever we learned from algebra, exactly similar sort of thing works here. Okay, so let's just understand this, how we can say all of this. Okay, so let's just do it. Let's say Z is, I can write it in terms of complex thing, R cosine theta plus I sine theta. Okay, if that is your Z, and let's say I will also write W. W is capital R. The length of W is capital R, and the argument is phi. Let's just start with this thing. So I will start with let this is true. Yeah. Then what happens? De Moivre's theorem. You remember what is W power n? Therefore, W power n is Z, right? Z. So that will imply that R power n cosine n phi plus I sine n phi is nothing but R cosine theta plus I sine theta. Right? By our definition, this is always going to be true, right? So therefore, if you take the modulus on both sides, just the length, so this is a complex number, this is a complex number. If you take the length of those two, you can see that R power n is always going to be R, small r, and this is real. So essentially from here, what do you get? R is nothing but the nth power of small r. Yes, this is real. Yes, positive real essentially. So this is what we are going to do. So R and R are positive real. Are positive real. Positive real. Okay. Now you see, I also want to talk about the argument. So what is the argument? Also n times phi is nothing but theta plus 2k pi. Yeah, 2k pi. K is in natural number. K is in Z. Okay. Since these are the arguments, this is always true. Yes. Okay. So in that case, what happens? Therefore, what do we get? Phi. Phi is theta by n plus 2k pi by n. K and Z. Okay. K and Z. Okay. Now you see, if K is in Z, after n, you see this is a small remark. After k equals to, so you see it becomes, so if you take k equals to n plus 1, after that what happens is you are actually going to again end up with 2 pi multiples. So 2 pi plus pi. So you see, if k equals to n, let's say, yeah, what are you going to get from this particular term? Let's just look at this term. So you are going to get 2 pi. For k, so essentially what is happening is, in that case, phi, if k equals to n, phi becomes, let's just write it up. Phi becomes theta by n plus 2 pi. Yeah. When k equals to n plus 1 also, you see what phi becomes? It becomes theta by n plus 2 pi by n times n plus 1, which becomes theta by n plus 2 pi plus 2 pi by n. Yes. So you see, all of these additionally, what happens is you are actually adding a 2 pi after that. So essentially the total number of values which you are going to get, you are essentially going to get this. So let me write it properly here. So the values, you are only going to get the values for k equals to 0, 1, 2 and n minus 1. So n values you are going to get, because after that all of these becomes plus 2 pi, essentially the same thing. Yeah. So therefore nth root of z, what happens to that nth root of z? That you can write it as nth root of r. Yeah, remember capital R is nth root of r, and then you have cosine of theta plus 2k pi by n plus I sine of theta plus 2k pi by n. Okay, so this is what you are going to get. On what is k? K equals to 0, 1, 2 up till n minus 1. And after that, what happens is it actually gets the exact same thing plus 2 pi. So essentially it will be the same thing. Yeah. Okay. So you see now, small details. This is just the argument part, right? Now, if you want to find the principal value, so the principal value, okay, of w, which is nth root of z. What is the principal value? This is corresponding to okay, k equals to 0. Okay, so basically the principal value of argument essentially, yeah, and that will give you the exact principal value of the nth root. Okay, right. So let us take one example and see what happens. So let's say I have nth root of example. What is the example? So the example is this. See, I want to find out z equals to 1, let's say. Z equals to 1. Yeah. How does that example now looks like? You are basically trying to find w such that w to the power n equals to 1. You are trying to find all possible w's where possible w in C. Yeah. Such that w power n equals to 1. Yes. Now, of course, mod z is r, which is 1. So therefore mod z is going to be r, which is going to be 1. That is always true. And the principal argument of z is going to be 0. That is quite simple, right? Yeah. Therefore this formula, let's just call that star gives. Okay. What does it say? It says that the nth root of 1 essentially is nothing but, if you put all this formula together, it is cosine 2k pi by n plus I sine 2k pi by n. Okay, that's the formula. And where is k here? K is nothing but 0, 1, 2 up till n minus 1. Yeah, very, very simple. So this is called the nth root of unity. Yes, I hope this is very simple. Yeah, and the thing is, if you take, let's say n equals to let's just say 4. Yeah, now what happens is I want to find what is 4th root of 1. So that will be nothing but plus minus 1 plus minus I. Okay, so 4 roots. Nth root of 4 is nothing but 4 roots, which is plus minus 1 and plus minus I. Okay, I hope this is clear. Now, what does this geometrically, let's just look at geometrically, what does it say? It says that, see, mod z is essentially r, which is 1. So we have all the nth roots are on this circle. Yeah, all the nth roots are in this circle. Yes, and they lies on 1 part. So the first root is 1. So the first root lies here. What about the second root? The second root, so this is 1. Yeah, the second root is I. I is where? Here. What about the third root? The third root is minus 1. You see, 1 I minus 1, and the fourth root is minus I. Okay, so you have 4 roots which all lies in on this unit circle. What out? So in general, notations, we also write it as 1 w. This is w square. Yeah, this is w cube, and this is w4, which is 1. Yeah, so we end up with this. Yeah. So you can do that, but anyways, the roots are essentially this. Don't worry about all this w and all. You can just do it like this. So it is how many roots are there? It is 1, I, minus 1 and minus I. Yeah. So with this, I am going to end this video. Thank you.